Hi everybody, welcome back to the lecture Computer Animation, today about physical simulation and ordinary differential equations. My name is Gerald Schuller. So, physical simulation is needed for physical animation and dynamics. And these dynamics describe the change of the motion quantities, displacement, velocity, acceleration under the influence of forces in space, for instance, gravity. Right? If we have an object and we let it fall, then it is accelerated according to gravity. And that's something that we can simulate in our animation. So if you want to have a realistic animation, we also need to simulate physical properties or forces like gravity. So subcategories are dynamics of rigid bodies, then the dynamic of deformable bodies, non-rigid bodies, and particle systems, for instance, fluid and gas simulation, tissue simulation, or hair simulation. So this is done based on Newton's basic law of mechanics. Right? We want to simulate the real world, so Newton's laws describe the real world. For instance, the inertia of bodies with mass, force, mass and acceleration, like this falling body. Then the law of effect and counter-effect. Then the impact of processes and conservation of momentum. Then work, energy and power, like movement, deformation, and for instance springs, which have forces on the body, and force fields like in gravity. And special features are the basic laws that can be put into effect as desired, like natural constants that can be adjusted. Like, for instance, you can simulate gravity on the moon in this way. Right? So that's something that you cannot do just making movies, but you can do in virtual reality. Yeah, so first the dynamics of rigid bodies. So the application of a force to a rigid body causes acceleration, but not deformation. So here we have the definition of masses and mass distributions and forces like gravity coming from a gravity or from a spring, for instance. Then we have boundary conditions, for instance, the restriction of freedom of movement, like collision detection. And we would need the numerical solution of Newton's basic equations, like force equals mass times acceleration. Right? So you can put this into this so-called differential equation. The acceleration is the second derivative of the place x with respect to time. So this is the acceleration, and this acceleration is the force divided by the mass. Right? So basically we bring mass on the other side, then we have mass divided by force divided by mass equals acceleration, and this leads us to this equation here. Right, so here we have our first differential equation, because it's an equation using the second derivative here, and we need to solve this equation in order to have how a body moves in space. So x is the place in space that we need to solve it for. Yeah, and we need to evaluate the positions and the motion states for each frame. Yeah, so the simplest case is that the body concentrates its mass on just one point. Right? It's not distributed, we just have a point mass. In real bodies, however, we have a distribution of the mass within their volume. So here we would have the volume, and then r is the distance from some center point. And here we have center point here, and we basically would concentrate the mass on the center point, and r is the basically the vector which points to this center point. Right, so this is basically the equation to compute this center point. Yeah, so we have a rotation with unrestricted freedom of movement around the center of gravity and otherwise according to some restrictions. So this is basically how we can simplify a distributed mass in this volume and describe it as a point of mass, right? And this is the vector which points to the center of gravity basically, or the center of mass. Yeah, and if we have rigid bodies and two bodies collide, then the penetration of those two bodies is often not desired, right? So basically they collide and then they have some behavior in the case of collision. So prerequisite here is the detection of the collision. And for that we need to determine the intersection of potentially colliding bodies. So first we have a pairwise rough determination via the bounding boxes of the objects. So these are easy to compute. And subsequently, if we detect there might be a collision, there we need to have a detailed analysis for the affected bodies. So we have a collision detection, which is very computationally intensive, and it becomes more complex with increasing geometric complexity. So that's why it's better to use simple geometries. So here we have some examples. 3 ways of contact. We have colliding contact, bodies approaching each other. Then we have a resting contact, bodies move past each other. And then we have a separation, bodies move away from each other. Right here we have those cases. Here we have a colliding contact, so body A is colliding with body B. It has some force, and then we need to decide what to do. Here we have a resting contact, so body A slides along body B. And here we have separation, body A moves away from body B. Yeah, so we have not only contact points, but also contact lines or contact surfaces possible. And we use a reduced contact set to reduce computation time. For instance, edge vertices of the cut surfaces. We have a change of velocity and angular velocities according to the law of conservation of momentum. And we have a calculation by a numerical solution of differential equations, like we just saw, right? But this can be very costly, and the question is, how accurate does it need to be? And also, do we have numerical stability? So that's the question that arises by using differential equations. Do we have a stable solution? So we have a simulation of deformation under the action of forces when we have deformable bodies. Right? We have a deformation during a collision, like a crash. Then we have hanging down fabric or clothing. So this is very deformable, right? If you have fabric like on a table or clothing, like a jacket, this is actually very deformable, and it's still desirable to have a realistic simulation for a realistic effect. So this requires the modeling of the internal physical properties of the object, like the fabric. For simplification, often we use spring mass models. So this is often used for fabrics. Basically, we have concentrated points of mass which are connected by springs. So the mass points within the body are connected with springs, and then we have a simulation of forces and their application on those mass points. And we can use the numerical simulation using finite element models, which often means we have high computational complexity. Yeah. So here you can see a symbolization. So this fabric consists of those concentrated mass points which are connected by those springs. And this is what we use for modeling fabrics. Yeah, so the dynamic simulation of such a system consisting of very many, usually independent points, individual objects. And these objects can be point masses, but they can also be more complex geometries. So application examples here are not just fabrics, but could also be water or fire or smoke or fog or clouds and snow or rain, right? So this particular rain, you can easily imagine we have those raindrops, and they behave according to the Newton dynamics, right? So the display of it is often as so-called billboards. Normally it's always directed to the camera. Yeah, then we have particle systems. So particles can be emitted from any surface, and typical properties of these particles are a position and a rotation. So we have a vectorial velocity, we have color, transparency, and texture, and we have a size of those particles and the age and the lifetime. Right? For instance, if you have smoke, those particles emit from a fire, but then they die after a certain lifetime. Yeah, and these properties can be influenced via animation and dynamics. So here are some examples. This example comes from Star Trek 2, the movie, and this is the Genesis effect. So here you have some planet and you have some sort of outbreak here, volcano or something, and you can see it emits particles, and those particles are then dissipated into space. Here you can see a close-up. So here you have a surface. The surface emits particles. The particles change over the lifetime and then they die. Here's an example for tissue simulation. Here you have a tablecloth, right? So this is on top of the table, and then at the side of the table it hangs down. And basically here we have this tablecloth modeled as those point masses and springs. Yeah, so the approaches here are deformed geometric surfaces, a physical simulation, and particle systems. Here you can see a mannequin having cloth. Here you have collision detection. So here we have the collision between fabric and this avatar, and the collision between the substance with itself. And here we have a high geometric resolution necessary to get a realistic simulation. We have a fast collision detection via distance fields, and we have fabrics with different properties, for instance silk, cotton, velvet, and so on. So they have different physical properties. And these garments are made from sewn pattern pieces from different types of fabric. So that's also possible. Yeah, then hair is another kind of fabric. So here we have three essential aspects. We have a geometric modeling of the hair. Then we have the physical animation, the dynamics of hair, and we want to have a realistic rendering. So for the geometry, we take approximately 100,000 to 150,000 long, thin cylinders, which leads to a very complex model of hair. So that means we have a high computational complexity for the dynamics and the rendering. And we have a varying complexity for short hair or fur or long hair or frizzy hair or curls. Right. And there are different methods for the simulation. We have explicit hair models where you have many thin cylinders. Then we can model it as a cluster or wisp. So basically this reduces the number of objects. Then we can use the cantilever beam model. So we have a reduced number of those beams. We can use a flow rate or also particle systems to model hair. So the explicit model uses each strand of hair, which is calculated and animated individually, and hair consists of several segments of equal length. The hair first is radially on the hairy surface, like the head, and gravity bends the hair down. The advantage here is intuitive and realistic, but the disadvantage is that it needs a high computational complexity and high computational effort. Yeah, so somewhat simpler is this cluster model, also called a wisp model. The idea is that adjacent hairs have similar properties and only some leading hairs are computed, the key hairs. And then we have an interpolation of the remaining hair from those key hairs. Right, so that's reducing the computational complexity. So the key hairs represent the surrounding hair tuft. So here's an example. Basically, you model fewer hairs and then you just interpolate to neighboring hairs. Yeah, then we have the cantilever beam model, as you can see here. So here you also have a simulation of a bunch of hairs, and the bunch is basically this cantilever here. So we model hair as elastic rod clamped on one side on the head, and this deformation is based on the bending moment and the shear force, for instance from gravity. Then we can simulate hair as a flow. So here we are exploiting the similarity of hairs with field lines from flow fields. Right, so it emanates from the surface, the head, and then behaves like a flow. So those flow elements are the current, field lines are parallel, they have a source, field lines originate at the head, and then we have vortex field lines which are closed, and hair runs along those field lines. You can see it, so it's modeled like a field, a force flow, and you can also see it curls. So in this way you can model the inherent forces of the hair with limited complexity. Yeah, and you can also simulate it as a particle system. Here we represent the hair as a spring mass system, and we have a static particle system, which means we have no emission and lifetime is infinite. Yeah, and we also have dynamics. So here we have a spring mass system for each individual hair, and we have a collision calculation of individual hairs with each other and with other objects. So overall this is very computational, complex or intensive. And the rendering is also highly anisotropic. We have alias problems due to the fine structure, and therefore we need a subpixel rendering with subsequent resampling. So hair simulation can be simplified for very short hair, like fur. So here's an example. Or here an example for fur. Here's an example for longer hair. So this is actually a very complex simulation here. Yeah, and this also leads us to artificial life, which is a simulation of the behavior of larger number of living beings. So examples are crowds or flock of birds or a robot army. And this is a particle system with additional properties, like a definition of the behavior, like collision avoidance, same speeds and directions of movements, like a flock of birds, and can be extended by more complex algorithms and methods from artificial intelligence, like, for instance, fish. Right here you have a flock of fish, and here you have a predator, a shark, and then you can program how the individual fish behave to get a realistic behavior of this flock of fish when a predator approaches. Yeah, and this also leads us to scripting. So scripting, the objective is fast development, few formalisms, and a simple syntax. It's good if it's interpreted, which means no compiling is necessary. We have implicitly declared variables, automatic type conversion, automatic type garbage collection. And this also leads us to the scripting with Python, for instance in Blender, which is an open source animation program. And it also contains a game engine in which function blocks can be programmed with Python. And I can also show a Blender example. Okay, so that comes in a moment. So here's the Blender example. You can easily install Blender in Ubuntu because it's open source with sudo apt install Blender, which I don't need here because it's already installed. So in this case I just started with Blender %, and here you can see it starting. And it's actually quite a complex program. And to just mention scripting, you can open here. And then it actually starts a interactive Python console. So it's like the usual Python console, except that you have additional objects here that you can use. So here you can just type 1 plus 3. So you can see it gets 3. So it behaves like the normal Python console. Yeah, so that's actually very convenient, but it has a somewhat steep learning curve. So if you want to do some complex animations, this is actually very good. But it takes some time to learn it. Okay, so let me continue with the lecture. So let us now talk about ordinary differential equations. Right, so we just saw that we need at the core of the simulations ordinary differential equations. We need to know how to solve them. So how do we solve and implement differential equations, like this equation for the free fall, for instance here? Second derivative of x with respect to t is force divided by mass. So this force F could come from a spring, like this mass spring model for fabrics, or in the case of a free fall of an object in a gravitational field, it would be the gravitational force. And this gravitational force is G. G is force divided by mass, and G is the gravitational constant. And on Earth, it's 2.81 meter per second square. So this is an acceleration, right? So this force accelerates any object with this value. Yeah, so here we have this equation that we need to solve for our body, for instance in the free fall. And in general, an ordinary differential equation can be written in this form. We have a derivative, the first derivative of here some vector x, that's why it's boldface, is a function. So this function is also has a function output. So this depends on the vector x and the time t, right? So this is just the first derivative, but observe that we can also obtain higher order derivatives, as in the above example where we have a second order, because we have this vector form, right? So for instance, the second order derivative can be written using this vector x with two entries. So it consists of two entries here, x0 and x1. And basically x0 is the original x and x1 is the derivative of x0, right? So here basically we can hide the higher derivatives in this vector then. And then basically this differential equation turns into this form, dx to dt. Here we now have this higher order derivative is f of x. So then we just need to have some function of x0 and x1 here. Right. So the goal for solving an ordinary differential equation is, given a starting point x0, find the path and movement x of t. Right? For instance, we have an object at some point of space and then we let it loose and then it falls down, right? Accelerated by gravity. So we want to compute how it moves given this differential equation. So how do we solve it? And a tool for the solution is the so-called Taylor series, which you can read more about here in this Wikipedia entry. And the Taylor series is basically describing any function as a polynomial, basically of infinite order, but you can also make a finite polynomial out of it and then add an error term. And this error term here depends on the order +1 of this polynomial. Right, and that also means this this is basically a function of this power, and that means if you have a high order here and h is small, then this becomes quickly very small. Right, so you want to have a high order here because then you can make h small. If it's smaller than 1, then this disappears quite quickly. Right, so here this is the Taylor series of order n. And this O of h of n is the error term and a function of the order of h of n here, right? So this is just for estimating how accurate this Taylor series representation will be. So ideally we want to have a high order here for good accuracy, but for practical reasons we want to have a low order because then it's easier to calculate. So it's conflict. But we can also see that if you have a low order here, we can still get a low error if we make the h sufficiently small, right? So there's a trade-off between how small we make h and how large order we need here for the polynomial. But then if you have a small h, then we need more time steps here. So again, that would lead to higher complexity. So again, it's a compromise. Yeah, and here this notation x to the n here means it's the nth derivative. So here x to the n means we have the nth derivative at time point t0. Yeah, so basically here this already tells you how to estimate the function depending on time, right? Here we have a starting point, x of t0, and now plus some h, right? So we can predict where this object is after a time h, right? A little bit into the future. So then we can apply this estimation here, and then the result becomes our next t0. And then again we can look a little bit ahead into the future, step by step, iteratively. Yeah, so we just need to choose an order n and keep h sufficiently small to keep the error term O of h to the nth power sufficiently small. So the simplest choice here for complexity is n equals 1, which leads us to Euler's method. Right? So that's actually quite simple. So when you look at this expression here, if you just have n equals 1, then just one term stays. So here, then we would have the term for n equals 0. So here h would then be there, and then we would have x, 0 derivative, so that's x itself, x of t naught. Here we have n factorial for n equals 0 is 1. So for n equals 1, we just have x of t naught times h. And for n lowercase n equals 1, we have, well, actually in that case, this h would disappear because h to the 0's power is 1. So, but if for n equals 1, then we would have this h, and we would have the first derivative of x, and here this n factorial would be again 1. So that leads us to this expression. So here lowercase n equals 0 gives us this term here, x of t naught, and then here lowercase equals to 1 gives us this term, h times first derivative at the position t naught, and then this error term. Right, and actually this error term should be h squared. And the same down here, because h is already covered by the sum. Okay. Yeah, so this is the Euler's method. And remember, the differential equation told us that the first derivative is our function f. So we can just replace it here. So this is then our iteration. So the next point of the object is computed as the previous point plus h times the function f plus some error term here. So then there is the adaptive step size method, which estimates this order term O of h. So it should actually be squared. Okay, that's better. So this adaptive step size method basically estimates this error term and chooses a sufficiently small step size h to keep it sufficiently small. Right? So we just make the h just big enough such that we don't worry about this error term. And this will change according to our function f here. Right? If you have a function f which changes quickly, then we want to make this h small. If this f changes slowly, then we can make this h larger. So we can adapt it to the concrete function. You can also read more about it here in this Wikipedia article about adaptive step size. So in this way we can neglect the error term, which then leads to our final expression here. So the next point is the previous point plus h times our function f. And this is done iteratively such that t naught plus h becomes then our next t naught. There are also higher order methods which also reduce the error term, like this so-called midpoint method, which is a second order method with n equals 2. So then we keep more of our Taylor series. Or the Runge-Kutta fourth order method, which is a fourth order method with n equals 4. And you can read more about them in these Wikipedia links. And for that, they estimate the higher needed derivatives by sampling the first derivative f at different points in t. So basically, you take those samples, take differences, and try to estimate the higher needed derivatives for those higher order methods. So they are more complicated to compute, but for the same step size h, they give more precise results. Yeah, but for now, let's stick with the Euler method. So there's actually a nice JavaScript example here at this website here. So let me just open it. open it. And here you can see there's this little JavaScript example where you can just choose a starting point in this flow field. Imagine this would be like flowing water, and this flowing water exerts some power at some point which is swimming here in the water. And now we can simulate the moving path of this object using different Euler methods with different step size. So here step size 1, and we can just say start, and then we compute from here. The flow field takes this h equals 1, and then we end up here, and so on. So here next step. And when we have smaller steps, we will get less error. So here you can see we need many more points to calculate, but we get smaller error, and we can actually compare it with the actual. So this would be the true solution, which is this dark blue. It's actually quite close to Euler 0.125, but a little bit off from this coarse step size. So the smaller we make the steps, the more precise the answer will be, but the more complex the computation will also be. We can also display all Euler. Let's see here. The smaller the step size, the more precise it becomes. Okay. So with a midpoint method, which means a Taylor approximation of second order, we usually get a better result than with the Euler method, even with a half step size, where the computation complexity is identical. So often actually it's worthwhile to use the midpoint method. So the midpoint needs twice as many computational steps as Euler with the same step size, thus just as many as Euler with half step size. Yeah, but still often midpoint is better, even with the same complexity. So this shows that it's usually worthwhile to either use the midpoint method itself instead of the Euler method, or to use adaptive step sizes. So usually actually that's the best, to use adaptive step sizes. So here's a numerical example. So let's take this very simple ordinary differential equation. So the derivative of a function y of t is f of y comma t, and that's the function itself. So here the derivative of the function is the function itself. And we can solve it by application of the Euler method to this ordinary differential equation. But first we need to choose the starting point. For instance, y of 0 equals 1 for t naught equals 0. And we choose the step size, for instance, h equals 0.4. And then we get y for the next time, t1 equals 0.4, by just inserting it into Euler. So here we see it. y0 plus h times y prime of 0, and that's 1 plus 0.4 times 1 is 1.4. So that's now our solution for t1. Now we go to t2. So y of t2 is y of 0.8, so basically 2 times h. This is y of t1, which is what we just found, plus h of y prime of t1, and that's 1.4 times 0.4 times 1.4. So this is again our h, and the result is 1.96, and so on. And now we can compare it to the true solution, the analytical solution for this case. We just solve it by assuming that y of t is of this form, c times e to the xt, with some constant c, which depends on the initial value, and a constant x. So plugging it in results into the solution. Y prime of t is x times c times e to the xt, and that should be equals y of t, which is here the original function. And comparing the two, we see that x needs to be 1, right? And if you want to have an initial value of 1 for t equals 0, we also get c equals 1. and that means our searched function is y of t equals e to the t. So for this simple case, we could find the analytical solution so that we would not need the numerical approximation above because we know the solution. But in general, this is not necessarily possible, and then only the numerical solution remains. So here we can also compare the exact with a numerical solution using Euler's method. And here you can see the two time steps. And here's the true solution if you plug it in. And this is what we got from Euler's method. 1.4 instead of 1.49 and 1.96 instead of 2.2255. So this shows the inaccuracy of the Euler method if the step size h is too large. Right? So here in this case h was kind of large. Yeah, so this leads us to the next example, a Python example for our case of the free fall of an object. So we can implement our example from the beginning, the free fall of an object, with the ordinary differential equation d square x to dt square equals f over m, with f over m equals the gravitational constant of 9.81 meter per second square. Yeah, and this is a second order ordinary differential equation which we need to turn into a first order differential equation with a vector of dimension 2. So here you can see it. So here we have our x, the vector of dimension 2 consisting of two elements, x0 and x1. The first entry is the original x, and the second entry is its derivative with respect to time. And when we look at it, this derivative with respect to time is just the speed v, velocity, right? So the vector consists of the place and the velocity. Yeah, and that means the derivative of it would be here the first derivative and then the second derivative. And this would be given by a function and its velocity. And in this case, the second derivative is our constant g, right? So this is given because of our free fall condition here. Yeah, so v is the velocity, the first derivative with x with respect to time, and a is the second derivative of x, the acceleration, and g is our gravitational constant. So this is actually our acceleration here, and g is the acceleration, which is our gravitational constant. Yeah, so now we can apply Euler's method to it. So here we have the step x of t naught plus h equals x of t naught plus h times our vector function of x and t naught. And we already saw that this f is v and g, so fairly simple in this case. So here it's v of t naught, right, because that's depending on the starting point. And g is constant, so easy enough. So here we now use a starting value of the speed of v of t naught equals 0. So at the beginning, the object is holding steady in the point. And in Python, we can write it as a NumPy array. So x, here I'm using capital X because in Python we have no boldface x. So capital X is 0.4. 0.4 is our position at the beginning. That's our x. And here's the velocity, 0. So here's the starting point x for x and v for position and speed. Here g is the gravitational constant, minus 9.81, minus because here in Python we have the gravity pointing downwards, so that's why it's negative. And here is our step size, 0.05. And here the step size, which is in seconds, is basically the time equal to the time of a frame in our simulation. Right? I chose the frame duration also to 0.05, which is about 20 frames per second. So here, this gives us a real-time simulation. Yeah, and then I'm using the actual computation in the display function of the display function of our simulation in OpenGL. So here we have our function f. So again, I'm using capital F instead of boldface F because here I don't have any boldface F. So that's our array here, x of 1. That would be our v. And here's the constant g. This is then the Euler step, x plus x. So this is the x of t naught plus h. This is the x of t naught plus h times f. Right, so here the old x and this is the new x. And from this new x, we take the first entry, the x, and this is actually the vertical coordinate, so I call it y vert, which I'm using then in OpenGL for the display. Yeah, and then we can let it run. So before I let it run, I open it, copy. So this is actually based on gedit based on our solid cube light with animation. So here you can see our display function, and in the beginning I'm also importing time for the frame duration and numpy. Here I'm setting the starting values of x. So here the position and speed is 0. Here the gravitation constant, and here the Euler step size. And here the position for the display, which takes the first entry. So here's the display function, which defines here the virtual camera. And here the position. And here we have the translation function. So here we have the translation according to y vert. So this is the vertical position. X is 0, which means it's in the center. And the z coordinate is 1.0, so that means it's about a meter away from us, a virtual meter. And I'm using a solid teapot. So it's not a cube, but here it's a solid teapot. It looks nice, I think. And here's then our function f that we just saw. So this function, which is the derivative, and here is the Euler step, right? And then it extracts the vertical coordinate as the first entry of x. Yeah, and that's it for the display. And then it also has this idle function. And this idle function just basically does the sleeping for one frame period, and then it redisplays the frame. And both are called here in the main section. You can see it's down here. Here I'm having again the lights, so they give nice shadows here. And here I have the display function, and here the idle function, which is basically just doing the sleeping for one frame period and the redisplaying. Yeah, so let's take a look how it looks like when I execute it. Python 3. Yeah, and you can see it's doing a falling, and it's actually quite quick because it's real time. So to make it slower, I can actually go to slow motion by changing the step size. Instead of the real-time 0.05, now 1/10 of it, right? So this is basically a 10 times slow motion now, making those steps smaller. Let's try it again. And now you can see the teapot falling in slow motion. So let me do it again. Yeah. So here now it falls in slow motion. And you can also see that it accelerates down, like in a real gravitational field. Yeah, so that's basically this. So you can also try it yourself with different age and see how it looks like. Okay, so that should be it for today. Thank you for your attention, and then have fun with the experiments.